Hello everyone. In this video, let us talk more about wire part. So wire itself by itself is a physical has got some physical dimension. It has got some width as well as length. And this particular section of the wire we have taken out from a practical circuit that we were learning in some separate section of videos. So this is a practical wire. This is a real wire that we have taken from a chip, and let us try to analyze do some analysis on that itself, so that will give a practical feel of what we are exactly doing, and whatever we say, that will make more sense if we do something on a real wire. So we have this wire over here, and we said that the wire has got some physical dimensions. It has got a finite length and a finite width. So whenever anything has got a physical dimension, there is some finite fixed amount of resistance and capacitance that is associated with that particular wire. In this case, this wire, we can replace this particular wire by a bunch of resistance and capacitance across the wire. So if you see, there are small resistance and capacitance that is connected in series, and this particular RC network are then again placed all over the wire. So this is just a representation of the wire that we have. So wire can be represented in a form of an RC network. That's what we wanted to mention over here. So what we'll do is we'll try to model. So over here there are three parts. So the first part is the clock port from which we are sending the clock signal. Again, this, if you see, this is again having a small or a finite dimension. We'll come to that part. So we have the clock port, the first part. The second part, we have the wire itself, the complete wire, and the third what we have is the load. So every flop which is placed over here, there is a flip-flop which is placed over here. It acts as the load to this particular network. So it's simple as saying in these words that this particular clock port is driving this load which is sitting over here through this particular RC network. So it's as simple as that. We can talk in this format also. So these three parts, let us try to break these three parts in three different sections. So we will approximate this section as the first we have the clock port over here, which is present over here. The next we have the load, which is nothing but the input capacitance of the flip-flop which are present over here. So that will determine as load. And the next we can approximate this complete wire, this whole section of the wire as a single lumped RC network, of which we can say the R0L and the C0L are basically the R0 is the per unit length capacitance, and C0 is the per unit R0 is the per unit length resistance, and C0 is the per unit length capacitance. This what we can model, or we can approximate this whole bunch of network into a small one. So first of all, let us try to clearly define what all these terms are all about. So we have this length. L is the length of the wire. So let's say we'll take one section of the wire and call it as length. So this is the length of the wire, L. Next we have R0 and C0. So R0 and C0 are per unit length resistance and capacitance. So for example, for this complete length, this is 1 unit of length. So 1 unit of length, the resistance and capacitance for 1 unit of length will denoted by R0 and C0. So basically R0 into L will be the resistance of the complete wire. C0 into L will be capacitance of the complete wire. It's as simple as that. If we just taking one unit or one section of the wire and calling it as R0 and C0 per unit length resistance and capacitance. Okay, so next we have, so R0L and C0L are the total resistance and capacitance. It is just a simple multiplication of the per unit resistance with the complete length of the wire, and per unit capacitance with the complete length of the wire. It's as simple as that. We are just multiplying things over here. So this particular section is very important, because we will be using L and all these terminologies in the next sections. So yeah, so these are the terminologies which are associated with this particular network. So now that we have approximated things over here, what we'll do is, also this particular clock port, or let's say this particular clock, we said that this again has got some finite dimension, so there will be some resistance which will be associated with it, and let us call it that RD. So this will be your driver resistance. So let us call it as driver. This is the load, and this is the RC network, or this is the wire. So this is a very good model to understand the complete RC network. So you can see how have we simplified the complete complete clock tree, one of the complete clock tree section, into some finite resistance and capacitance over here. So now it becomes very simple to analyze this network and come up with some solutions for buffering. Let's try to look into that. So let's move it in this direction, and let's try to analyze only this part. So what we have is, if you actually see the total time constant, that is the RC time constant, let us try to calculate that. So for the R part, let's focus on the resistance part. So you have two resistance which are in series, which is RD and R0L. So two resistance in series will just add up. So it will be called as RD plus R0L, and two capacitance in parallel also adds up. So it's so basically capacitances in series are behaves very similar to resistance in parallel. So capacitance in parallel gets added, and resistance in series gets added up. So this is the capacitance C0L plus the load capacitance. And now to find out the RC time constant, we have to multiply the resistance factor by the capacitance factor. That's all we need to do. So let us find out the RC time constant over here. So we have RDCL, we have this particular term which is multiplied by L, and we have this the unit capacitance and resistance which are multiplied by L square. So if you see in this particular equation, the dominant factor what you see over here is the L square. It's a proportional of L square. So if you look into the time constant value, it's actually a function of L square. So what does this equation actually means? When we say the time constant is L square, it means the time required to charge the output load capacitance with this particular length of wire is proportional to L square. So the larger the value of L, the more time will be required to charge the output load capacitance, and to quantify what will be that value, it is a proportional value of, it is proportional to L square. So greater the L, the magnitude of time that is required to charge the load capacitance will be a function of square of the length of the wire. So that, which is very huge, and that's why you see all those bad transitions at the output of the clock port. So that's the reason that you're seeing the transitions which are going worse from when you go from the clock port to the clock endpoints, as we saw in the last video. So this is the reason, because the time constant is actually a function of L square. So clearly we have a culprit over here. The culprit is L square, and we have to try to break this L square into different parts. Let us try to control this L square and see what we can do. Okay. So we have this L over here. So in conclusion, we have this we had this clock tree network over here, and we had approximated this clock tree network as an RD, which is RD is nothing but the clock port, the driver resistance of this particular clock port. R0L and C0L are nothing but the per unit length resistance and capacitance multiplied by the length. So R0L denotes the complete resistance of this particular wire, and C0L denotes the complete capacitance of this particular wire. And load was nothing but the flip-flops which are present over here, the input load capacitance of those flip-flop. So this is very important. It's very important to conclude what we did in the upper slide. So this is what we are doing, and this is we modified this particular network into a small RC network, and then we made a conclusion that the time constant. So by time constant I meant the clock port, the clock signal which is being sent over here, the time required for that particular clock signal to make an effect at this particular flip-flop, the time required for that is L, it's proportional to L square. So the larger the L, it will be square value of that particular L that will take it is that particular amount of time that it will take for the input signal to make an effect at the clock port, at the clock endpoint, which at the flop clock endpoint. So you see the impact is L, it's not L, it's L square. So this slide is basically the reason behind having those bad transition of the clock tree. So now what we'll do is we'll try to since I'm running out of time, what we'll do is we'll try to insert a buffer at the center of the wire, exactly at the center of the wire, and see how does it impact the following equations, and how does inserting a buffer, what are the limitations and what are the advantages of inserting a buffer at this particular point, and see how does this equation change. So let us try to look all this in the next video. Thank you.